In this video, I introduce a generative world model for autonomous driving. Generative world model takes the video, text, and action as inputs to generate realistic driving scenarios by mapping the inputs to discrete tokens, and then predicting next tokens in the sequence through learned understanding ability of environment dynamics. As shown here, this context images is conditioning. The model uses context images and conditioning to generate the future images. The world model can generate videos by performing future rollouts starting from a video prompt. Accurate future prediction enables the accurate vehicle to plan its operation actions. The autonomous driving model consists of two components, namely the world model is an autoregressive transformer that predicts the next token condition on the past image, text, and action tokens. The input image, text, and action are first encoded into a shared d-dimensional space, and the concatenation is then used as input to the world model. The video decoder maps the predicted image tokens back to the pixel space at a higher temporal resolution, as shown here. This is the input, including image sequence, actions, and text. This image encoder, action encoder, and text encoder. This is the d-dimensional tokens in the latent space. The world model uses these tokens as input to predict the output tokens, and then the video decoder uses these image tokens to predict the future videos. Image tokenizer first discretizes input image as patches that are used to trade off between the sequence length and the vocabulary size. The sequence length refers to the number of the discrete tokens that are needed to describe the data. The vocabulary size corresponds to the number of possible values a single token can take. The patch is more thematically meaningful than raw pixels, as shown here. This input image, and this one patch with resolution of 16 by 16. Image tokenizer uses this image as an input to generate the token vectors. This is the sequence length, and this vocabulary size. And then these tokens are used as an input to the Deno model to generate the tokens that are input to the world model. Likewise, in character level, the input text has a longer sequence length, and each individual token has a smaller vocabulary size with little meaning. However, if using word-level tokens, the input text has a shorter sequence length, and each token contains a lot of semantics, but the vocabulary size is extremely large. The byte pair encoding is a trade-off between them. Denoising diffusion model is used as the image decoder condition on the image tokens obtained by discretizing input images with the pre-trained image tokenizer. During inference, the model is a condition on the predicted image tokens from the world model. The decoder is trained for video generation by using previously generated context images and conditional tokens generated from the world model. If the denoising diffusion model is denoted as a E-state, the noise prediction objective is defined as here. This is a noise video with A alpha t prime and sigma t prime function of t prime that defines a noise schedule. E is a denoising target, and t prime sampled from a uniform distribution U is a discrete diffusion time, as shown here. This talk is from the world model. These are generated images and video. For more details, please check with these references. Thank you. Bye.